This is the intro video for AP Calculus AB, section 4.2. We're going to be looking at area and talking about how to approximate the area under a curve. So we're going to look at a couple of different sums in this video. The first one is a left sum. So what I want to point out to you is that we've got a curve, a graph of a curve here. It's represented by the green graph, and you can obviously see that it's, a curve goes up then down. And what I've tried to do is I've tried to approximate the area between that curve and the x-axis with some rectangles, and I'm specifically using left sum rectangles. These are rectangles whose height is determined by the left side of each interval. So you can see that the height of this first rectangle is determined by that left side of the interval. There's another left side, so on and so forth. And then of course over here, as we move to the other end, we continue to use the left side of the interval to determine the height. So let me get rid of those lines real quick. And so this is called, because it uses the left side of the interval, this is called a left sum. They're rectangles that we're using to approximate the area under the curve. We're using the left side of the interval. So to find the area, to approximate the area, what would we do with all of those rectangles? Of course, we would add them up. So that's what goes in the blank right there. And then thoughts on accuracy. First of all, it's not perfect, right? You can see that there is, some space here, some space there, and then of course right here we have some extra area over the curve. And so, I think we can look at this picture intuitively and decide, well, it's not going to be perfectly accurate. It'll be okay, but it's far from perfect. One other note on accuracy. Did you notice that on this part of the graph over here, did you notice how the green graph is increasing? If I use a left sum, which I am here, on a graph that's increasing, I think it would be safe to say that the sum would be too low. So I'll put, on increasing functions, a left sum is too low. And then if you look at the right side over here, you can see that the green graph has now transitioned to a decreasing function, and so you can see that those rectangles are above the graph. So if you have a decreasing function, then a left sum would be actually too high. All right, we're going to look at two other sums here, the right sum and the midpoint sum. Let's focus on the right sum first. A right sum is an approximation for area using rectangles whose height is determined by the right side of each interval. So if you compare this back to the one we just looked at, you can see how it's the right side of the interval that determines the height of each rectangle versus the previous one, of course, was a left sum. So this time we're using the right side of the interval to determine the height. And as before, if we wanted to try to approximate the height, we would take all of those rectangular areas and we would add them up and get the approximation for area. So thoughts on accuracy, again, kind of like the left sum, we can see this is going to be inaccurate, right? I mean, there are some sections big sections where we're missing area, and then there are some other sections where we actually have too much area. There could be some degree of balancing out there, but I think we can see it's not going to be perfect, right? It's not going to be exactly accurate. And then on this stretch, notice how the blue graph is decreasing. On sections where the graph is decreasing, then a right sum is actually going to be too low. You can probably see that with those rectangles being below the blue graph. So it's on a decreasing function, then the right sum is going to be too low. And then of course on an increasing section of the function, then a right sum is going to be a little too high. All right, and then finally we have the midpoint sum. The midpoint sum is essentially the average of the left sum and the right sum. And so the midpoint sum is going to use rectangles whose height is not determined by the left end or the right end, but by the midpoint of each interval. So I've tried to represent that as best I could on this graph. You can see that the height of this first one is right in the middle of the interval. I missed a little bit with the next one there. But then, it's right in the middle there, roughly right in the middle there. I'm using the middle of the interval to determine the height of each rectangle. So, like I said before, in order to approximate the area, we would take all of those rectangular areas and we would add them or sum them up. Thoughts on accuracy? This is probably, so far the most accurate. We're not going to be able to make a judgment like we did before on, increasing and decreasing, being too high or too low. That really only applies with right sums and left sums. But a midpoint also is something we would be expected to do, and we'll practice one of those here in just a second. Okay, so our first one says use a left sum and 3 rectangles to approximate the area of y equals 2x squared plus 5 on the interval 1 to 7. Use a rough graph and a table to help find the left sum. So I'm going to do a rough graph here. Y equals 2x squared plus 5 is going to be a parabola. So here is my attempt to graph this parabola. Plus 5 means that it's been shifted up 5, and then 2 means it's a little bit steeper than the parent graph. I'm just going to go with something like this. It's a little lopsided, but I think it'll work for our purposes. And the interval we're talking about is 1 to 7. So I'll put that on the graph as well. Let's say that this is 1, and then way out here is 7. Okay, so it asks us to use a left sum and 3 rectangles. So we need to split up our interval from 1 to 7. We need to split it up into 3 subintervals. Think about how wide those subintervals would have to be. Since the distance from 1 to 7 is 6, if I want 3 rectangles, I think each of them is going to have to be 2 wide. So I'm going to make this a 3 and this a 5, and that will give me my intervals. I'm going to use a left sum. So the left sum would look something like this. So I draw these rectangles in. Please notice I'm using the left side of the interval to determine the height. So just as a general thought here, can you see how this sum is going to be too low, right? Because we're talking about a left sum on an increasing graph. And so once we find our approximation, we can be for sure it's going to be too low. All right, so I don't know if I'm going to do a table or not. I think I'll just set this up with these rectangular areas, and we'll kind of look at how a table might work when we have class. So I'm going to find the area of each rectangle. So I'm going to shoot for this first one to begin with. So I'm going to say the area is approximately equal to, of course, each rectangle is base times height. So for that first rectangle on the left, think about what the base length is. The base length should be 2, right? From 1 to 3 is a length of 2. And then the height is going to be the height of the function, the height of the red graph, when x is 1, because we're using a left sum. So we can use our function back here to help us understand what that should be. We could write 2 times 1 squared plus 5. That would give us the actual height of the rectangle when x is 1. I'm just going to plug the 1 in. That'll give me my y value, which is the same thing as my height. So I'm going to move on to the middle rectangle now, right there. So this one's pretty similar, right? It has the exact same base length, so it's going to be 2 times, and then I got to put the height in there. The height is not going to be the height of the function at 1. It'll be the height of the function at, I hope you just said 3. So to find the height, it's going to be 2 parentheses 3 squared plus 5. This will give me the height of my rectangle, and of course multiplying by the base will give me the area. And then finally I'm going to move on to the last rectangle here. So it's going to be plus, and the base once again is 2. The height will not be based on the function value at 1 or 3, but it'll be based on the function's value when x is 5. So it's going to be 2 parentheses 5 squared plus 5. At this point I just have a little bit of arithmetic to do to finish this off. So area is going to be approximately equal to 2 times, I think, 7 plus 2 times 23, I think it would be, right? Yep. Plus 2 times 55 for that last one if you do the arithmetic. And then, of course, if we add those up, it's 14 plus 46 is 60 plus 110. I think we end up with 170. I did that in my head, so forgive me if I made a little mistake there. Okay, so 170, that is our approximate area under the curve, or you could say between the x-axis and the red curve there. And we know for sure that that is an underestimate because on an increasing function, a left sum will always be an underestimate. Okay, let's take a look now at number 2. So like before, we're going to use a graph here to kind of help us understand what's going on with this. So we'd have a graph of sine of 1/2 x. You know, we can do this without a calculator, but if you want to use your calculator to see what's going on, that's fine. What this would look like, we've got sine of 1/2 x on the interval 0 to 2 pi. And so what that 1/2 does is it stretches this graph horizontally. And so when we think about this graph, it would actually look like this as we go from 0 to 2 pi. It stretched out sine horizontally. It made it wider. So this says use a midpoint sum and 4 rectangles. So 4 rectangles means 4 subintervals. So I need to split this 0 to 2 pi up into 4 little sections. So one right here, split that one up, split that one up. Let's think about how wide each subinterval would be. If I do the halfway mark would be pi, and then this would have to be another halfway mark, so that would be pi over 2, making this 3 pi over 2. Okay, so I'm going to sketch in some rectangles now, and these rectangles are going to be midpoint rectangles like it asked for. So these are a little bit tougher to draw. I'll do my best. I would say that first one on the left there would look something like this. Notice how I use the middle of the interval to determine the height. And then maybe this one, something like that maybe. And then this one would actually be almost the same height. My scale is a little bit off, please forgive that. And then this one would be, like that. Okay, so we are going to use those rectangular areas to approximate the area under the curve, and so they should look something like this. Area equals, I'm going to do the first one. So let's think this through. The base length is going to be 0 to pi over 2, so I think the base length is just going to be pi over 2. That should be true of all of these. So the height, we are not going to use the height of the function at 0. We are not going to use the height of the function at pi over 2 because we're not doing a left sum or a right sum. We're doing a midpoint sum. So let's think this through. What would be the midpoint, the x value of the midpoint of this interval? It would be right smack in the middle right there. It should be pi over 4. Pi over 4. So what I'm going to do then is I'm going to use the value of our blue graph to determine the height of this rectangle at pi over 4. So it's going to be sine of 1/2 times pi over 4. I'd plug in a pi over 4. I would not plug in a 0 or a pi over 2 because that would be a left sum or a right sum. I'm doing a midpoint sum, so I'm going to plug in pi over 4. Plus, it's going to be the next one over here is going to be our next rectangle. The base is pi over 2, and the height is not going to be the height at pi over 2 or the height at pi. It's going to be right in the middle there. So that point in the middle is going to be 3 pi over 4. So I would write sine of 1/2 times 3 pi over 4. So that's going to be my input. I'll put that in parentheses. Put this other one in parentheses too. That'll give me my height. There is some symmetry here, but I'm going to continue to try to set this up the rest of the way. So the next one right here is going to have a base length of pi over 2. They should all have a base length of pi over 2. The height here is going to be sine of 1/2 times the height right here is going to be based on 5 pi over 4. So I'll put sine of 1/2 times 5 pi over 4. And then I'll have to squeeze this one in down below, the last one here. So this would be pi over 2 once again for a base length. And then the height would be sine of 1/2. The number we're going to use here to find that height would be 7 pi over 4. So 1/2 times 7 pi over 4. Okay, so at this point we'd use our calculators to actually figure this out. So feel free to do that. I'll do the same thing. We can compare our answers in a second. Just one little note here. Please don't be too concerned about all the little details here. We'll do some stuff like this, but we'll gradually transition to where we would use a table to help us do something like this, and we'll look at how to do that in class. So I'm going to figure out what the answer to this is, and we can compare and see if we got the same thing. Okay, so plugging that into the calculator, I got area is approximately 4.105, if you round off to the thousandth place there. And whether this is an overestimate or an underestimate is kind of hard to judge because we used a midpoint sum, but we do know that it would be a relatively accurate, depending depending, definition of accurate here, relatively accurate approximation for the area under the curve. So when you come to class, we'll look at some other ways how to do this, but if you've got this, you've got the basics, I think you should be in good shape.